Dr. Nimya, please start.
Okay, sir. Good morning. So I'm presenting an overview of statistics. So this is basically from an oncological standpoint. It is mainly designed to help people analyze a journal or an article. So the topics I'll be covering will be descriptive versus analytical, case control and odds ratio, cohort and relative risk, randomized control trial, intention to treat and per protocol analysis, meta-analysis, hazard ratio, confidence interval, what are the graphics used in statistics, how to read a forest plot, and Kaplan-Meier curves. So, a basic introduction. Study design is the arrangement of condition for the collection and analysis of data to provide the most accurate answer in the most economical way. So basically the study designs can either be observational studies or interventional experimental study. So observational studies are basically just reporting the outcome. The investigator does not introduce any new parameter, just simply observes what happened. Whereas an interventional experimental study, the investigator intervenes in some way. So just a brief heading. So the observational study, it can be descriptive study, like case report or case series. And under analytical studies, we have ecological study. Uh, Ecological study, it is a population-based study, and cross-sectional case control and cohort comes under the analytical study. Then we have interventional study, which have randomized control trial, cluster randomized control trial, fee trials, and community trials. So ecological study, it is basically population-based, example, the nutrition of an entire population, etc. So I will be starting with the case control and the cohort. So again, how I said, descriptive only there'll be one group. In analytical, there'll be two groups will be compared. So in a descriptive, we are just reporting. There is no explicit hypothesis. So descriptive epidemiology, that is case series and case study, is used to generate a hypothesis. That is, if there is a high incidence of cancer found in smokers, there'll be multiple case report on it, and finally we suspect that there might be a correlation between cancer and smoking. So then we will do an analytical epidemiology where there'll be two groups in which they are compared. So in under analytical, we can accept or reject a hypothesis. So going into case control study. So case control study is a method of sampling population in which cases are identified and enrolled. So and the matching is done. I will show you the figure. So basically for a case control study, at the time of taking the data, it starts with the cases. That is, at time T0, there are people with cases. And then we go back and inquire whether was exposed or not exposed. So when to conduct a case control study? When the disease has a long latent period, like example, cancers or cardiovascular disease, or when the disease is rare, example, studying risk factors or birth defect, or when the exposure data are difficult to obtain, like pesticide level, whatever be the reason, that is at the time of time T0, we have already the diseases present in the population. Then we are going back and seeing the disease. So it is used to find the exposure rate and controls to the suspected factors. And from this, we get the odds ratio. Odds ratio, it is a measure of the strength between the risk factor and the outcome. So I'll tell you the pitfalls of a case control. So in the odds ratio, I am taking it a very brief overview of all topics. I hope I'm not going into the in-depth details of each. So how we calculate the odds ratios exposed into unexposed and disease and no disease. So it is odds ratio is odds that was the case was exposed, that is AD by BC. So odds ratio, how do you interpret an odds ratio? People who smoke, I'll go to this. Okay. So how do we interpret? The odds ratio, it can, while telling a probability, it can be any value between 0 to 100, but the odds ratio, it is usually listed from 0 to 1. So the larger the odds ratio, it is more likely the event is related to the exposure. So if the odds ratios, like how we tell hazard ratio, if the odds ratio is 1 or close to 1, it suggests no change in the frequency of exposure. That is, there is no correlation between the exposed event and the suspected disease. So the odds ratio 1, that is with the higher increase in, there's a higher chance of disease happening in the group, and the odds ratio less than 1, it suggests a reduced risk. So, okay. So how do we list the values? If an odds ratio of 1.2 means there is a 20, we subtract it from 1. So if an odds ratio of 1.2 means there's a 20% risk in the odds, that is from 1, it is 0.2. So there is a 20% increase in the odds of the outcome with the given exposure. And odds ratio of 2 means there's a 100% increase in the odds of an outcome with the given exposure. So again, but the thing to remember is that the odds ratio, we already have the disease. So we do not have, we are not prospectively seeing the data. It is the retrospectively seeing. So we can just say the odds that the person has a disease is this much. So it is not attached to time. So if a smoker, there is a odds ratio of 1.8, it just suggests that for a person who smokes, there is 80% more chance of the person having a higher chance of lung cancer with smoking. It just means that there might be a suggesting factor that smoking causes the particular cancer. Okay, so the odds ratio is 2.5, then it means there's a 2.5 times higher likelihood of having the compared outcome. When we tell it in percentages, it will be 1 minus 2.5. That is like 125 times more chance, 125% higher likelihood of having the outcome. It is just a likelihood. It is not a definite risk ratio. So the advantages of a case control study, it is inexpensive and it is only suited for diseases which have a long latent period. It is well studied with a rare outcome. And the disadvantages, again, like I said, it is not a good method for a study of rare exposure. Don't give any idea of incidence or prevalence. It only gives an odds ratio. And there can be various types. It is a retrospective. So depending on the people, they can be having information bias, recall bias, and observer bias. So the main example was the thalidomide was discovered using a case control. So for a factor to cause a disease, a set of factors must be met. This is called the Hills criteria. So the cause must precede the effect. So and the association should be plausible. That is, the result should be biologically sensible, like smoking causes cancer. And there should be consistent result from a number of studies, that the same result should be in a multiple study, and the association between the cause and the effect should be strong. That is, using a odds ratio, we cannot tell a factor will be definitely causing the disease. And there should be a dose response relationship with the effect. That is, higher levels of the effect should lead to a more severe disease or a more rapid disease onset. That is, if the dose increases, like a person who smokes more should have an equal and higher chances of having lung cancer similarly. And removing the factor of interest should reduce the risk of the disease. That is, if the person stops smoking in COPD, like if the person stops smoking, will the risk of the disease be reduced? So these criteria must be met. These are called the Hills criteria. If you have to definitively say a agent is a causative factor for a disease. So the biases in case control study, they are the biases due to confounding. That is, the same factor might be affecting both the exposure and the disease. And the memory or recall bias, like a person who has a disease may be more likely, it is a retrospective data. So a person who has more disease may be more likely to recall the exposed agent. And the selection bias, people might select it differently, and Bergsonian bias. Sometimes the same agent might be, multiple people might be exposed to it, but they may not be getting admitted into the hospital. So when we take a hospital data, it might be slightly skewed. And the interviewer bias, like the people might interview more the people with the disease agent. Then the cohort study. It is comparing individuals with a known risk factor with others without a risk factor. It is looking for disease over a period of time. Distinguishing features are that at time T0, there is no disease. That is the difference between a case control and a cohort. We are at the time of T0, we do not have a disease for the patient. And the defined study group are observed for a period of time. So at time T0, there are people without disease, and then we have the exposed and the not exposed, and then we find out how which patients among the exposed had the disease and which patient did not have the disease. So the cohort studies are called prospective, but the thing is that I will go into detail later. So even though we can have ambispective cohort, that is from the past we can take people, but at time zero still they would not be having the disease. That is the difference. So it can be ambispective or retrospective cohort studies can be there. And cohort study, the use is that it is in a prospective data. That is, earlier at time T0, the patient had disease. So we are just taking a specific subset of people and then choosing whether looking at them whether or not they were exposed or not exposed. Here we get a wide variety. Like even in the exposed, there will be people having no disease. So it is a more accurate representation of the real world. Okay, an example is if the induction period, this is useful in cases when there is a long time duration between the exposure. Like we'll need to follow the patient for a longer time period. Example, induction period of leukemia or thyroid cancer by radiation. So here, again, there are like different types of cohort. Like in the past, we take a group of people who did not have, like, for example, if the patient had radiation, we can take that group of people, but we are following it throughout to find second malignancy. In that case, at time T0, none of the patient have second malignancy, but at a later time point in the future, they might or they might not get. So still, it is called a cohort study because at time T0, there is no disease and we are following up the patient. Or we are taking the data from the past. So it is like a retrospective, like the time period from where we have taken as retrospective. So there are two, three parameters we can identify from a cohort study. So one is an incidence rate. Incidence rate is the rate outcome among the exposed and the non-exposed. So the incidence of disease in person with exposure, incidence of people, that is the number of people without the exposure, that is the incidence rate, and the estimation of risk. So we have the relative risk, that is the incidence of disease rate among the exposed divided by the incidence of rate among the non-exposed into 100, or the attributable, and we can also find the attributable risk, incidence rate among the exposed minus incidence rate among the non-exposed divided by the incidence rate among the exposed. I'll just go into it in detail. So again, with the calculation, it is A by A plus B divided by C by C plus D. That is the incidence rate among the exposed by the non-exposed. So again, like how we told the odds ratio, it is that if the risk ratio is 1 or close to 1, there is no difference in risk, there is no association. If there is a risk ratio is greater than 1, it indicates a positive association. That is, then exposure have higher chances of causing the disease. But here, compared to the odds ratio, it is that the significance of the value is higher. In odds ratio, it was just a probability of it happening, whereas in risk ratio, there is a direct risk that shows that as the exposure increases, the disease outcome might increase if it is greater than 1. Similarly, if the risk ratio is lesser than 1, it is like if a nutritional supplement is given, it reduces the risk of the disease. Again, with odds ratio, it would just be the probability or the likelihood of having it is decreased, whereas in a risk ratio, there is a definite reduction in risk with using it. So it can be used as percentages or as numbers. So for risk ratio of increased by 1.37 times means in percentages, it will be 1 minus 1.37. It is like more than how much percentage? That is like 37%. Again, a relative risk of 0.8 means 1 minus 0.8. So that will be like 20% reduction in risk. So a relative risk again of 3.37 would be 1 minus 3.37. That will be like 237% increase, risk of disease is increased, or in numerical terms, the risk of disease increased by 3.37 disease. So in odds ratio, we do not use the term risk, but in a relative risk, we can, when it is a relative risk value, we can actually use the term risk. So how strong is the association? So when a relative risk is noted, I will go into confidence interval again later on. If the p-value is more than 0.05, like if the p-value is more than 0.05 or the confidence interval includes 1, a relative risk won't be statistically significant. So even if for sometimes, let us say, if smoking, if a study showed the relative risk of smoking with cancer is like 3.37, but from the study we found that the p-value is not significant, it still would not be considered significant. That is, the relative risk would not be considered significant. Again, from the population, like the confidence interval, the relative risk confidence interval, when we get, if the value includes 1, it means that at the point of 1, there is an equal chance of either happening. That is, there may not be a correlation between the disease, the exposure and the agent. So again, we would consider it not significant. So again, odds ratio and relative risk. Odds ratio is just the odds or the probability of that event happening, that the odds of probability of an event happening, whereas relative risk is an actual risk. And the thing is that in the general rule, if the prevalence of the disease is less than 10%, the relative risk and the odds ratio may be the same. That is, the rarer the disease, it might be both similar. Again, like I said, related risk is usually done in prospective. The importance or the usefulness of relative risk is that time is taken into account in relative risk. That is why it attains more significance. In odds ratio, incidence is not used for risk calcification, and it can overestimate, because we are at time t0 we have the patients with disease, so it can always overestimate the risk of a disease, especially in rare diseases. Again, the advantages of cohort and okay, this you might know. Again, it is time bound. There is no recall bias, and it is in a prospective. Most of the times, it's in a prospective direction, and the results, there is lesser number of biases in a cohort study. So again, this just repetition of the same. So depending on the study, depending on what we are investigating, that is, if it is a rare disease or rare diseases, it may be very difficult to do in a cohort. So we tend to do a case control. And if it is testing multiple effects of a causes, everything else cohort would be slightly better. So depending on what we are trying to find out, we should use the corresponding study. And the confounding factors that are there, selection bias, recall bias, it depends upon the study. There might be more bias in one study than the other. I hope it is clear. Do you have any doubts?
You're going a little fast. If you can slow down a little bit, I think people may have some questions as we go along.
Okay.
Ma'am, I want to understand once again the relative risk, the ratio, and the correlation as well.
No, it is just, I was just taking part by part, because I will be talking about hazard ratio later. I didn't want to mix everything confused. So odds ratio is just the odds or the probability of a thing happening. Like, let us take not smoking, alcohol. So alcohol, like they might find that alcohol, people who drink alcohol might have lung cancer. So, but the thing is that, and they, by any chance, they might have founder factor. So it will be that people who drink alcohol might have 1.2 times more chance of having lung cancer. But there can be like multiple other causes. People who drink alcohol might also be smoking. So smoking could have been a confounding factor which resulted in this thing. So odds ratio just tell there is a higher, not risk, higher probability that a alcohol drinking person might have lung cancer. Okay.
Okay, ma'am.
So, but when we do a relative risk, but when we follow an alcohol drinking person throughout, like when we take all people who drink alcohol, and then we are prospectively following the same group. Okay. Now we will find that all alcohol drinking person may not have lung cancer. Okay. I'm just
Yeah,
giving
ma'am.
you an example. So that, now when we take a relative risk, we might find that the relative risk may be 1. Like there is nothing correlating with alcohol and lung cancer. Okay, if we are doing it in the same study.
Yeah.
Okay, yeah. But in another case, let us take all smokers, and we are following them. We will find out that maybe smoking after like there is a relative risk of 2.5 times.
Okay.
So it means when we use a relative risk, we have like prospectively followed, like in a timely manner, we have actually followed all people who had exposed and non-exposed. So it is like a better parameter of risk. Okay. So
Okay.
now it is an actual risk. So that all people who smoke has an actual risk of having lung cancer.
Yeah.
Okay. The odds ratio, it is just a probability. Like the
Okay.
patient may or may not have, but higher
Mhm.
chances of having.
Yeah.
But in a risk ratio, relative risk, it is a definite chance, like very high
It's
likelihood
like
chance.
just quantifying how much percentage of
Exactly. Except in
okay.
odds ratio, we don't use the term risk.
Okay. Thank you, ma'am.
Okay. Okay, now we are going into experimental epidemiology. So there are like human and animal studies. We have randomized controlled trial. Randomized controlled trial is an epidemiological experiment. I will just go into randomized trial. All of you know what randomized trial is. I will just go into the basic details. So in a randomized trial, we have a reference population. From it, we have a inclusion criteria, and following it, we have an experimental population. And from experimental population, we have a study population. I'll just explain it to you. So a target, so first we have an experimental or the target population. So the reference population would be all people who have cancer, who have come into, if it is radiation department, all people who have cancer, head and neck cancer, who have visited the radiation department. That would be the reference population. From the reference population, we have the inclusion criteria. It is a maybe only if the reference population was all cancer patient, head and neck cancer patient, inclusion criteria would be a oral cavity or a oropharynx cancer of a specific stage, maybe stage 3, locally advanced oral cavity and oropharyngeal cancers would be a experimental population or the sample population. From it, we have the exclusion criteria, like people refusing and everything. So that denotes the final sample which we are analyzing for the study. Okay. Yeah. So now, and in the sample, there are several ways of doing the sampling. We have a systematic random sampling. That is some fixed fraction of the sampling frame. Like, so this is of a randomized control trial I'm talking about. There is a systematic random sampling. That is every 10th person or the 5th person will be allocated. For a random sampling, there will always be 2 groups. Like one will be an intervention group and one will be a control group. So how do we divide the study population? There are multiple methods. One is randomly doing it. Like the first person will be in the first group, second person will be in the control group, third, fourth, like that. Then we have the stratified random sampling. Stratified random sampling, it is done when we subdivide it into various parameters. That is, we divide it into age, sex, maybe some other, according to the Nordic stage, N1, N2, N3. So the first person, then depending on these parameters, we divide the people into the intervention and the control group. So we will input the parameters into the software and then divide the people. This is done so that the both groups will be matched equally. That is the stratified sampling. That is a person who has 55 age and N1 will be put into one group. So the next person who has a 55 age and N1 disease will be put into the other group. Then we have contact or consecutive sampling, in which just the first 100 people will be denoted into one group and the next 100 will be denoted into another group. So we have a study group and a control group. Yeah, this is the same thing I told. So when we are comparing, once we do the blocking or stratification, the use is that it gives a homogeneous stratum. That is, if we are doing a random sampling or just a systematic sampling, one group might have a slightly higher higher number of the disease. So maybe if it is nodal staging, one group will be having a higher nodal staging and one group will be N1. So all the confounding it can act as a confounding factors, and it won't be matched between the two groups. So stratification helps to create a homogeneous background in which we can analyze. So you can analyze the corresponding group. That is, if it is a nodal staging, N1 nodal staging can be compared, N1 nodal staging of the interventional treatment can be compared to the N1 nodal staging of the standard treatment. It helps in better analysis. And we have the parallel and the crossover design. In the parallel, you just have there'll be a sample, it will be randomized to control and treatment, and it goes parallelly. That is, the control gets its treatment, and the intervention therapy, it gets its corresponding treatment. In the crossover, after applying the first treatment, there is a washout period, at time where they are given off, and after which they are given the opposite therapy. That is, the control gets the new therapy, and the new therapy people get the control therapy, and then again we assess the response. So it is the same group gets both the treatment, so that it helps to assess it better. So it is like this: group 1, group 2, there is a time for elimination or a carryover effect. Then the group 1 gets the opposite, the next new treatment, and the group 2 gets the opposite treatment. So the use of this is that, like, sometimes in some diseases, there is always a doubt that one group is missing on a treatment, or if it is not matched properly. Yeah, especially in cases if the two arms are not matched properly, this helps to ensure that the same group can act as its own control. That is one use of the crossover study design. And then we have the manipulation, follow-up, and assessment. So again, you can have blinding in RCTs. Blinding is a single blind trial in which the participants are unaware of which group they belong. That is a study of control. And the double blind is both the investigator and the participant is not aware. And the triple blind is both the investigator, participator, and the analyzer does not know to which group they belong. And the blinding is done to basically to observe the bias, to decrease the bias. So that we have, like, I'm not going to too much details. Different designs of RCT. We have stratified RCT, crossover design, factorial design, cluster RCT, non-inferiority or superiority RCT. So, yeah, factorial, I'll talk about factorial alone. And in trials, we also use the term intent to treat and per protocol analysis. So what is intent to treat? Intent to treat is an analysis in which the patient to the group which they have begun treatment. Like in the beginning, you split it into two groups, like one has an intervention, like one has a new drug and one has the standard of care. So intent to treat is the analysis in which patients are analyzed based on the group to which they were allocated. So it is also called the gold standard. In it, the problem it is that sometimes, like, despite we might have put a patient in a particular group, but during the course of treatment, we might have found that, okay, if you're doing surgery for a patient, we had initially planned the patient for surgery followed by adjuvant chemo. And in the other group, maybe it was surgery alone. But maybe due to some patients' morbidity, we couldn't give the patient adjuvant chemo after surgery. But still, this patient will be analyzed in the arm where the chemo will be analyzed as a person who got chemo. Like, it will be analyzed in the same arm to which they were initially allocated. But the disadvantages, basically disadvantage is that it doesn't take into account protocol violation. The advantage is that it helps to give a actual look into how it is a more real world situation. That is, it can happen, like the patients might fall off the patient. It is a more a real world and thing of what is going to happen with patients. Yeah. But so what is the side effect is that there might be that it is going to give us a slightly far off result. That is, the analysis may underestimate the adverse effect. One second. Okay. Okay. So the good thing about it is that it analyzes, it gives a real world situation. That is, the patient, despite having an analysis, how it would look between the two groups. Then we have the, I'll tell the comparison later. Then we have the per protocol are as treated. That is, if the patient has, whatever happens in the analysis is taken into account. That is, a patient who has a patient who changed or patient who followed up are removed from the analysis or given to the arm which according to which the patient was treated. That is called a per protocol or as treated analysis. So this helps to give this helps us to show that even with all the so it actually helps to analyze whether that particular treatment is working. That is, if a drug is given and if the drug is working, we will be able to pick up correctly on a per protocol analysis. But this is like a very straightforward thing. Like, only if the patient is always following all the factors which was told in the trial, like all the parameters, and taking the drug properly, this will be applicable. In most of the situation, the benefit of having an intent to treat is that even if the patient is not following it properly or any other parameters that comes into it, because of the large subgroup of people, that effect gets computed out. So you will know that in analysis, so we always try to get the intent to treat. If the intent to treat is proven significant, it is always considered better than a per protocol treatment. So per protocol treatment we usually do when we don't get an intent to treat treatment significant. So it is again subject analyzed according to treatment taken or not, and usually as treated or is usually used if the intent to treatment shows no effect. So it is always better to have a intent to treat proven significant than a per protocol analysis. But the what the per protocol shows is that you can use the drug has a benefit. Like, if a drug is supposed to stop diarrhea, the drug might have a benefit as what is shown by a per protocol analysis. Then we have a factorial design. Factorial design, it's a kind of RCT in which multiple factors are compared together. That is, like, we can compare 2-3 arms, like treatment A and B can be compared. Like, it is a case of aspirin and beta carotene. Like, multiple combination can be compared in the same trial. That is aspirin and beta carotene only, aspirin only. So using the same study group, we can study multiple drugs. So the STAMPEDE trial was actually like a factorial. It was a multifactorial trial design. STAMPEDE for prostate. It used rituximab. It used RT alone. Then ADT. It used ADT alone. ADT plus cetuximab. Then ADT plus RT plus ADT plus docetaxel. It used multiple combination, and then depending on the result, they stopped each arm. So the basic analysis of an RCT, we get relative risk, attributable risk, absolute risk reduction, and number needed to treat. And the survival analysis also you can get from an RCT. Then we have a superiority, equivalence, and non-inferiority study. Superiority studies to determine the clinically relevant difference between, I will go into it, show it again. So the superiority study is used to show when there is a new treatment is having a better profile than the standard treatment. Then we use a superiority study when we are sure they are more effective. An equivalence study is used when the new intervention is neither worse nor better than the established intervention. Then we have a non-inferiority study in which a new intervention here we are in a non-inferiority study, we are not trying to show the new agent is better. We are just trying to show the new agent is not inferior. That is, if the patient has some issue, we can actually give this new treatment with acceptable side risk and profile with acceptable treatment effect. It is basically, it is not worse than the standard treatment. We accept that the standard of care is the actual standard of care, but this is like can be given. The patient may not have that much side effect and it is curative. This is what we are trying to show in a non-inferiority study. Again, any drug might be non-inferior, but you have a cutoff in a non-inferiority study. It shouldn't fall below the cutoff of curative option. Okay, I'll show that later. So now coming to meta-analysis. Meta-analysis pulls result from multiple studies. It is a review. It is basically an overview and a review of all the articles. So when we take a hierarchy of study design, we have the case report, case series, ecological studies, and all these are hypothesis generating. That is, from all these case report and everything, you get a hypothesis that something might cause a disease or some medicine might be slightly helpful in a disease. From the case control and cohort and the RCT, you have a hypothesis generating. You have a risk ratio or other parameter which shows that the parameters are causative or like affecting, or the medicine is working. That is how you generate a hypothesis to establish a causality between an agent. So if you take a pyramid of the evidence, the case control, case series, everything comes down. Then you have the randomized control trial. Then you have the systematic reviews. And on top of systematic reviews, we have the meta-analysis. So a meta-analysis is type of a secondary research. They themselves are not doing a research. You are compiling all the data and then analyzing the data from everything. So from you have an effect of estimate, risk ratio or hazard ratio, etc., and the overall treatment effect. So again, these are the parameters: odds ratio, risk ratio, absolute risk reduction, and the number needed to treat. Number needed to treat is the average number of patients that needs to be treated to prevent one additional poor outcome. That is, sometimes we say like of 20 breast cancers treated with post-adjuvant radiation, it prevents 5 deaths, like that. It is a number needed to treat to prevent additional death. So now from an RCT, we'll get a hazard ratio. So hazard ratio is time. Excuse me. Hazard ratio is the number need. Sorry, hazard ratio is the hazard in the treatment arm versus the control arm. It is the probability of that an individual at time t has an event at that time. So I'll just explain it again. So in a way, when you look at it, hazard ratio might seem the same as relative risk, but they are not technically the same. It is definitely different from odds ratio. That is a different thing. Odds ratio is a risk of proportion. It is just the probability, and the hazard rate is the hazard rate also has a time element to it, and it compares two treatments. It is a ratio of incidence rate. So again, like odds ratio, risk ratio, everything, it is again the same thing. One greater than 1 or lesser than 1. At hazard ratio 1, I will explain it, compare 3 again. Hazard ratio 1, the event rates are even in same in as many same thing. At a time t, there will be twice as many patients in the treatment group that are having an event. Or hazard ratio 0.5 means there will be half as many patients in the treatment group that has a disease. So how do you choose which parameter to use? So if it is like, it depends upon the type of variables, like whether it is a continuous variable or a binary variable or time to event. So binary variables like response, progression, decrease and reduction size, we can use a relative risk or an odds ratio. Like, as smoking causes cancer kind of thing, you can causes a relative risk. It is binary variable. There are only two variables in that parameter. Whereas a time to event survival, like time to progression, time to death, time to relapse. So there is a time element connected to what we are analyzing, whether it occurs at a particular time. Okay, so for that we use the hazard ratio. So again, hazard ratio, there is an how to explain? Okay, hazard ratio, it measures. There is always a timing attached to that event, and it compares two events. That is compared to if two subsets are given a chemo drug, whether with a hazard ratio 2.0 means that the patient who had the chemo drug will be healed twice as fast as those in the control group. At a time period of like at 5 years, this group will be performing better than the other group. If we denote the same thing, it will just be it will just be comparing one agent to the disease. Again, like I said, relative risk, it tells how the intervention changes risk. That is, a patient who has a chemo drug has a higher likelihood of the disease responding to it, whereas a hazard ratio tells us the exact value, like it at the time t, how much the person will be responding better than a comparative group. So it is always compared. Hazard ratio always will have one group that changes with relative to another. It is like two different groups will be compared in a hazard ratio, whereas relative risk, it is two parameters alone being compared. Hope it is clear. Hello? Any doubt?
Any doubts from the students?
No, sir.
So another example I'll just give you. When we are comparing a single agent paclitaxel versus a cyclophosphamide, so why is a hazard ratio required? Now that is a question. So hazard ratio, like sometimes it might show that an agent will be having a slightly median survival. Like again, all these are basically statistic based. So if it shows one drug is having a median survival of 34.7 and another is having a median survival of 25.8. But if the hazard ratio, so now you will plot the both of them in the graph. So it is basically hazard ratio is a risk ratio of one group to another group. So we have the hazard ratio of the standard drug divided by the hazard ratio of the new drug. So we have the hazard function for paclitaxel followed by the hazard function for the cyclophosphamide. So you can see for the standard drug cyclophosphamide, the hazard function is going in the upper graph, like the top line, and the lower drug is in the red line is the lower new drug which we are introducing. And you can see the hazard ratio is 2. So what it means is that even though the overall median survival, when we talk it, just denote the number, it shows the median survival is slightly higher. The hazard risk ratio 2 means that at any fixed point, the individuals in the therapy group are at twice at risk of death as the new drug group. I mean, here they have looked for this thing. Yeah, here they have referred for the toxicity, that is why. So at any particular group, the hazard ratio means at how much higher risk the patient is of morbidity or death or whatever was the parameter which was taken for hazard. Okay, the thing is that in a relative risk, you are just comparing 2 points, like whether this will cause a higher relative risk. In a hazard ratio, you are comparing 2 groups and how the 2 groups are interacting with one another. And now the new parameter that was introduced, like a new drug. So how do the 2 groups interact with the new thing? So there is always a time, it is time bound, and there is always 2 groups in a hazard ratio. And now we have the confidence interval. Confidence interval, it shows in what subset of values or in what range of values is our study result like applies to. It is the range of value that is likely to include the true population value, or how confident we are about the study's estimate. So now when we keep a bell curve, 95% confidence interval is the range which we can be 95% certain that the true answer lies. So it shows the limit to which our answer will be there, or to which how much we can apply our test result. So for factors like relative risk or overall risk, odds ratio, at the point 1, the relative risk and the odds ratio, there is no correlation. That is, there is no relation between the exposure and the agent. So if the range contains 1, it is considered. So no matter the actual value of odds ratio relative risk, if the value contains 1, it is considered non-significant. And because it means that at our actual population, it has the 1. I mean, there are times in a population where it is going to be meaningless, like the exposure is not going to cause the effect, like the disease or whatever, or the treatment is not going to be effective. That is, we have situations where the treatment is actually not going to be effective. Therefore, we do not consider it to be significant. So if the range do not contains 1, again, so it is considered significant. And in cases with difference like attributable risk, we use 0. So attributable risk ratio is attributable risk ratio is how much a factor increases the incidence or mortality rate of a group. Example, like it is again a calculator from the cohort study only. So a person who smokes, 18% of the if 20% of the people who smoke have lung cancer, but of it, if and 2% of the smokers, 2% of the lung cancer people are non-smokers. That is, like, there are people who can get lung cancer even without smoking. So now we calculate the attributable risk by subtracting the risk from the people who were not exposed but developed the disease. That is how we get the attributable risk ratio. We again get it from the cohort study only. So in situations like that, attributable risk, again, it is the 0 which is considered as a cutoff value. So in the previously said example, it would be like a smoker. So the attributable risk of smoking is 18% in total. That is, 18% of the people who smokes might have cancer, but there are like 2% of the people who may not have cancer. So in that case, we take the cutoff as 0. So in attributable risk, when we are seeing the confidence interval, 0 is considered the cutoff value. Now, again, in meta-analysis.
Can I just interrupt here? What I can see is you have reached halfway of your PowerPoint,
Yes, sir.
and we've spoken for 1 hour to us. I was just wondering, should we just digest what you have taught us today and reconvene next Saturday for the second half? Because then we would have sort of read and thought about it more, and we'll understand the second half even better if we do it next Saturday.
Yeah, can do that, sir.
Does that work? Because then otherwise, we'll have one more, like 2 hours of statistics. I think most people will find it difficult to digest.
Can do that, sir.
Should we take questions now, if there are any?
Does anybody have any questions?
Ma'am, I wanted to know about the hazards ratio, and also in the bracket which is written just after the hazards ratio value, the confidence interval. How to interpret that? The range which is written.
So basically, for doesn't matter whether it is a risk ratio, odds ratio, hazard ratio, the cutoff value is always taken as 1. Okay. So how we say is that, yeah. Okay. So for hazard, the term hazard, it can mean like hazard in the treatment arm or hazard in the control arm. It can mean depending on the what we are analyzing. So it can be like mortality, or it can be like
Relapse.
disease, death. So whatever we are calculating. Okay. So I will as an unofficial example, like I will tell, like odds ratio would be like in a road, if a person is traveling, he has he has maybe 2 times risk of getting into an accident, let us suppose. Okay.
Okay.
So odds ratio is just telling a probability that a person walking in a road might get into accident. But
Accident.
that
Okay.
is like may or may not happen. Like it is totally beyond the control. Like there is just a probability that any person who is walking might have an accident. Okay. So when we are putting it into risk ratio, it will be like we are more we have a attribute, like we have a time bound this thing. So it will be like we are getting more specific about it. So it will be like a person traveling on a cycle will have a 2 times risk of getting into an accident. Like we are slightly making it more like
Specific.
yeah, more specific. Like a person traveling in a cycle in this direction, like or who is getting a this thing will be having accident. So now we are making it like more specific. There's a higher risk of accident. Okay.
Okay.
Then, but in a hazard ratio, it will be like uh, a person traveling in a cycle will have a person in a traveling in a cycle in this time period, like for a period of like 1 day, will be having a higher risk than a person traveling in a car in the same day.
Okay.
You
So
understood? Like
time factor is also added in the hazards ratio.
yeah, time factor is added in hazard ratio, and also 2 arms will be there in the hazard ratio.
Okay.
Like you are always comparing with something else.
Control and that.
Yeah, control arm you are always comparing. With a risk ratio, it is just 2 points that are getting compared, but in a time bound fashion. Okay. Understood. So again, now we use the term 1. If it is greater than 1, it will be like higher risk or hazard or whatever. And if it is less than 1, it will be decrease in the risk. Like maybe if you're going in car, you have way lesser chances of getting into accident, like that. Okay. And if it is 1, there is no correlation. There is nothing happening.
Okay.
Understood?
Okay. And the confidence interval, which is written in the bracket.
So the confidence interval, it will be like, yeah. So you know that 1 is the cutoff. So if it, I can use the same example. So it shows that like, okay, maybe, okay.
It's spread equally in both the directions in this.
Yeah, it is spread equally. That is what. It is spread equally in both directions. That is risk ratio 0.78. It means the person might but it is between the confidence interval of 0. I'm using the first example. Okay. It's between the confidence interval of 0.55 to 1.5. So it actually means a person can even have a risk ratio of 0.35. Like we are just choosing the middle value. Okay, 0.78. But a person, for a particular individual, like all these are from study or trials which have a very large sample population. Like we have analyzed 1,500 people and got a risk ratio. Okay. Like it is from basically all the values are from study. But for an individual person, like a single individual, in order to apply the same result. Okay. Whether can we use a 0.78 is the question. So in the study, they found people who were having a risk ratio of 0.55, and they found people having a risk ratio of 1.5. So it means in some people it was not at all effective or decreasing the risk. Okay, decreasing the risk or mortality, whatever. Okay, but in some people it was increasing.
Okay.
But they just quoted the middle value, that is all. Okay.
0.78.
They just quoted the middle value of 0.78, but in some people it was actually increasing and some people it was actually decreasing. So
Okay.
if you are lucky, you might be in one group. If you are unlucky, you might be in the other group. You are not
Okay.
sure. So how can you tell, like, you give the chemo drug and it will work? Because you can be in any group.
Okay.
So that is why it is considered not significant. Understood?
Can I just say something and correct me if I'm wrong? What I understand from this is if there is unity, which is
If there is
unity, and then if your risk ratio or odds ratio is on the both sides of that line,
Spread equally on both sides of that
crossing,
one.
no, not equally, not equally. If it is crossing the line, then it will not be
that is
significant,
when
right?
we are using a meta-analysis, sir. This is just
That
a
will be in the
reporting
forest
of the
plot.
yeah, it is in the forest plot that will happen. Okay.
Any other questions?
Just one question from my side.
Yes. Yes, sir.
In your pyramid of evidence, the systematic reviews is on the highest side, right?
Top level.
It is meta-analysis above it, sir, actually.
No, meta-analysis, they have pulled it down. Just check once more. So my question is, we have discussed it even before many times. See, so why systematic reviews is on the top?
So I think they didn't. I might have cropped the picture. Meta-analysis is at the top of systematic reviews, sir.
No. So I mean, it is actually, so few of them, they write systematic reviews on top. Few of them write both meta-analysis as well as systematic reviews. So it is on the top. So my question is, how do you reflect onto it? Even if it is, say, number 2 above randomized control trial, say for instance, how do you explain that?
No, sir. The thing with meta-analysis, the thing with systematic review is that systematic review actually analyzes all the papers. Like, they will analyze the papers and they will, like, how much ever possible, they will classify it into, like, different subgroups or subset, like according to the result they get, and they just report it. Systematic review doesn't take into account of the factor that some papers might be having a lesser quality of evidence, like the inclusion criteria may not be stringent, or their the way they have analyzed the data may not be correct. Like, they might have included like, again, a paper, papers can be manipulated. If you know statistics well enough, papers can be manipulated in multiple ways. You can just report a per protocol analysis as significant and tell the treatment is valid, but the intention to treat might be lesser. So systematic review will just only give you a like a brief overview of everything, and they will just analyze based on this. This is what is told. But a meta-analysis takes into account how each paper is scoring on the overall picture. That is never done in a systematic review, sir. Meta-analysis has a second factor, which we heterogeneity of the sample and the overall effect of a single paper on the total sample is calculated.
Yeah, that's correct. So see, that's the point. So I mean, of course, we are not talking of the manipulation here, because let's limit the discussion. Otherwise, we know that manipulation can done even in RCTs. But let's address this statistically. The answer is selection bias. So we know that there will always be selection bias when you apply any non-randomized pooling. The problem here is, what I remember when I studied it for the first time, there was a clear distinction, and the top tier was always with the randomized trial as level 1A and meta-analysis as 1B, and few people would say it otherwise, the other way around. But systematic reviews, how they came up this chart, it is really baffling to me. So what I would say is that we should be asking these questions at probably all the forums. I have some answer to that why it has risen to the top in the last whatever decade or so, but that we discussed. But I mean, I think as students, we should keep asking. Whosoever reads statistics, we know for sure that systematic reviews cannot have same kind of evidence value as randomized control trial or meta-analysis. So there is, for me, there is no reason they can stand there on the top.
Yeah, I think, what do you say? Because systematic review can be very skewed. It just depends upon the individual person who is analyzing it. But the only reason I think it is on top is because it would be comparing 2-3 RCTs together. So
No, Nimya, RCT's comparison is with meta-analysis. If you are pooling RCT, it is strictly a meta-analysis. It cannot be systematic reviews. So in the name of...
no, sir, we can actually use RCTs and systematic trial reviews.
They started doing it. That's what I'm saying. So if you see the essential definition, by definition, meta-analysis was the pooling of randomized control trials. And that's why meta-analysis could answer more, could answer a question with more data points.
Precision.
Yeah. So what they have done is systematic review classically was something pooling of non-randomized studies. That was the essential difference between systematic review and meta-analysis. Now what they started doing is they are mixing and pooling up both randomized as well as non-randomized data and then giving inferences. That was the typical thing which Cochrane started doing. And that is my assumption, and that's what we've discussed time and again, that I think that's the reason systematic analysis, they tweak the words also sometimes. It's not systematic reviews, they would write some other word analysis or whatever. But essential feature is, what is the statistical feature? Statistical feature is you're pooling randomized as well as non-randomized data, which is clearly wrong in my mind. I mean, if you have pooled it, then your inference is flawed.
The thing with it is, on the same point, meta-analysis will always have to be done in a very structured way. Like systematic review, you can do without that much structure or the statistical this thing, but meta-analysis always have to be done in a very statistically correct way. Like you have to take each individual paper and split the data and analyze it properly.
Yeah, so I'll tell you. So the meta-analysis structured, why structured? Because simple thing that RCT, ideally you would know that there is a proper control mechanism or proper randomization. And if just for benefit for everyone, that when it started, actually it has both the content. So like as you said, that the paper based, and then there was something called as IPD based meta-analysis also, in which they actually used to approach all the trialists to get the entire data. So that is individual patient data-based meta-analysis that had the highest value.
Yes. Yes, sir. So it is always meta-analysis and RCTs. But the problem with RCT is that, one more reason why RCTs always get below meta-analysis is that RCT can be institutional, or like it is a very small sample of population. So any error that might have occurred in the RCT, you won't be 100% sure whether it can be applicable for the entire set of population everywhere. So that is why if a meta-analysis gives the same value, we take it with a bit more importance.
Yeah, it's a pooled data. Good. So I think rest of the questions we leave it for the next one. Thank you so much.
Thank you, sir.
Any other questions, or should we wrap up for the day? If there are no other questions, let's meet again on next Saturday, 10 o'clock. Thank you very much, Nimya. This was very, very useful. Thank you.